Hello everybody, good to see you all. Welcome to the first session of our geometry class here. So in order to start this things off, I'd like you to take a look at these four sentences that I've written here. I'd like you to consider them for a bit and just sort of think about what you note about them here. Any things in particular about these sorts of things, what they have in common, what they do not. Okay. So one of the first things you might have noted about these statements is that pretty much all these statements here they're stating something, and they seem to fall into one of two categories here. They seem to have something whether they're true or not. So for instance, number one here, this first statement, the product of two negative numbers is a positive number here. I think many of you know that this is going to be a true statement here. So we know, so in this situation here, we can label that this is going to be a true statement here. Now, why is it a true statement? That's something that we can discuss at a different time, but I think you already know that this is going to be a true statement here. The second statement here, this one is a little bit different. This one, of course, is referring to me. In this case, this also happens to be a true statement as well. Now, you may not necessarily know this off the top of your head, and I would hope you didn't, but you could find out what this. You can do a little bit of research, whether it's doing some digging into yearbooks or things like that, or just or just taking my word for it. You'll note that this statement is also going to be true as well. So we're going to note that this is a true statement as well. Okay. The third statement, on the other hand, I think you can see that if you have a basic understanding of how geography works here, this is going to be a false statement here, right? I think we can agree that this statement here is absolutely false. Iraq is definitely not a country in Europe. It's a country in Asia. All right. Now, the fourth statement, and some of you might know, wait a minute, there's something weird about this fourth statement here, right? We know that the first three statements here are absolutely true, absolutely false. But the fourth statement here, there's something going on about this here, right? Not to mention the fact that it is short, but it doesn't seem to, we can't really determine whether it is true or not here. There's something about the statement. And I'm going to come back to that here in a bit. So in order to do that, let me first take a look at a couple of other things here. Now, before we get to geometry, now I know that, when you think of geometry, you think of things like polygons, triangles, and, spheres, and all this other juicy stuff here. And I promise we'll get to that. But in order for us to get to that here, we need to start off with something pretty straightforward here. So what we're going to be looking at is this idea, what is known as mathematical logic. Okay? So in this situation here, you can just think of logic as the study of mathematical reasoning here. And in particular, we're going to be focusing on the branch of logic here that is known as Boolean logic or Boolean algebra, named after the British mathematician Boole, who was the first to really promulgate many of the rules or the ideas behind this sort of logic here. Okay? Granted, there are other kinds of logical systems out there, but we're going to focus on this because it's the simplest and the one that's going to be most useful to us here. You'll note that in this situation here, you can think of these as just sort of just another simple system to understand here. And, a system very similar to that of the system of arithmetic. You'll note that for arithmetic, you'll need some very simple things. In order to do arithmetic, you'll need two things. You need numbers, and you need operations. In the same way for Boolean algebra here, or Boolean logic here, you're going to need two things here. And I'll talk about the two things in a bit. But one of the things we're going to need is this concept of what are known as statements. So we refer to these statements here, these objects here as statements. They're the simplest units in logic here. These are the numbers of our Boolean logic system here. So things like what we saw in the initial page, those sorts of statements are things. Now, Boolean logic, what makes it different from the other kinds of logics out there, is that it was referred to as what is known as a two-valued system. And that seems a little bit strange, but when you think about it, it kind of makes sense. If you go back to the first three, we noted that the first three statements here, there are only two possible values. It's either true or false. This fourth statement's a little bit strange, and I'll talk about that again a little bit later on. But these first three statements all either resolve to true or false here. And that is the key of Boolean logic. And again, it seems a little bit like very obvious here, but it happens to be a very important thing for us later on. So Boolean logic is known as a two-value system in that each statement is either true or false. There is nothing in between here, what we call truth values here. A statement's either true or false. There's nothing in between. There are kinds of logics where you also have, you can also have a three-valued logic system where you can have a true or false that's sort of like a maybe. But that's something completely different. We're going to worry about that later. Now, going back to this here, we know that the first three statements here, these are our standard statements in our Boolean logic here because they result to true or false. So we refer to these as what is known as closed statements here, okay? So we can mention here that a closed statement is a statement with a definite truth value here. We know it's true or it's false here, right? So the first three statements here back in this, these were true or false here. We knew what they were, even if we had to do a little bit of research to figure out what they were. The fourth one, on the other, now we can actually go back to the fourth one here. We can see that the fourth one doesn't really work out too well because there's that big question mark here. This thing, it, right? You have no idea what it refers to here. This statement, as you can see, is we can't resolve it to true or false because we don't know what it refers to. So this type of statement is the second type of statement in Boolean logic here. We refer to this as what is known as an open statement. It's a statement here that does not have a definite truth value. We don't know whether it's true or false because there's some sort of ambiguity in the statement. There is a variable. In this case, the word it. It's a variable in the statement. We have no idea what it refers to. So right now, considering this, it is red, we don't know what it is, okay? However, we can very easily turn this from an open statement into a closed statement here by simply, adding specific things here. So, for instance, we can replace the word it. We can throw out the word it and replace it with other things here. So, for instance, I could say this pen, and I think you can see here this pen. If I say it is this pen, so I can say this pen is red, and I show you this object here. We can see that this closes the statement because we know that this statement is now false, right? Because this statement, this pen is definitely not red, right? On the other hand, this pen, you can see that this pen is absolutely red, so that will make the statement true. Now, of course, this pen is not the only object that makes this open statement true here. We could have many other objects, for instance, human blood, for instance, or other sorts of red objects here. And we refer to this as what is known as a solution set. So any objects that make an open statement true, we refer to that as part of the solution set. Now, we'll take a look at some other things here later on, but of course we have these things here that refer to this idea of what's known as a solution set, okay? So that's going to be our thing. Alrighty, so let's go back here to this statement. Iraq is a country in Europe. Now, one of the things about us mathematicians is that we mathematicians are actually not very, we are very efficient people. A lot of people like to call us lazy. I like to say that we're efficient. We like to write as little things as possible here. So, in general, these statements being the fundamental units of our logic system here, we would like to write a way to write them a lot faster here. So what we're going to do is we're going to actually assign a variable to them. So in this case, I can say, for instance, that I'm going to call the statement here P. Oops, this pen doesn't seem to be working anymore. Let me try the mouse. We can use the statement P here, and I can say that Iraq is a country in Europe. So this here, as you can see, so we can call this statement P here and state that every time we use the statement P, every time we use this statement, Iraq as a country in Europe, we'll call it P. Now notice at this point that this statement is false. It has a truth value of false. I like to make it a truth value of true instead. So if I want to do something if I want to make it true, what could I do here? Well, there are several things we can do. For instance, we can replace some of these words here. So I can replace Europe with, say, Asia, and say Iraq is a country in Asia. I could replace the word Iraq with something that makes it true. So for instance, I could say Hungary is a country in Europe. Another thing that we can do, and probably one of the simplest things you can do, is we can add a very simple word here, right? We can say that Iraq is not a country in Europe. So notice how here, even if we did not know anything about world geography here, by inserting this word not, we seem to have taken the statement and we seem to sort of flipped it on its head here. We know that by inserting this word not here, it changes the truth value from false to true here. And that's going to be really important to us here. So remember how I mentioned before about how with logic, we have we have our statements, which are the basic ideas behind it. Those are akin to the numbers in the arithmetic system. Well, we're going to need some operations to go with it here. So just like operations in arithmetic that will operate on numbers, we're going to have operations or operation equivalents here that'll work on statements. And the first is the one that sort of we just discussed here, this idea of what is known as the negation. So the negation here, ladies and gentlemen, looks something like this. We can see that the negation is going to be the key word here, is going to be the word not, N-O-T here. We can just simply insert it into the sentence to make it grammatically correct, and we express this idea of negating here. The symbol for this, you'll note that in this case is going to be the little squiggle here. Sometimes, if you look at older textbooks, especially if you're a computer science person, sometimes you'll see what looks to be like a reversed sideways capital L here. Now, note that in this situation, when you have something like this, you can just simply write it out like this. We can have something like this here. We can simply read this as not P. So for something like this, we can put the squiggle in front and just call it not P. You don't have to give it a specific name. You just call it not P. Now, as we mentioned, negations turn a false statement to a true statement, right? We started off with a false statement, Iraq is a country in Europe, and we turned it into a true statement here. Presumably, it would make sense that if I started with a true statement, such as Hungary is a country in Europe, if I put a not in it and say Hungary is not a country in Europe, that would make it a false statement. So presumably, the negation turns true statements to false statements and false statements to true statements. It's pretty straightforward, right? That's a little long. So again, we would like to be efficient here. What we're going to do is we're going to express what's going to go on in this, in what is known as a truth table here. So you can think of a truth table as just a chart that we can use to express every possibility here for a logical statement. So our truth table is going to look something like this here. You're going to note that this is actually going to be one of our very simple truth tables here. There's going to be these columns here. This first column here, this represents the original statement. You always want a column to represent the original statement here. And that's the first column. The last column here is going to represent the target statement. This is the statement you want to learn more about. Okay? Now, the one thing about a statement here, P. Now, P, remember, P can be anything. We gave a name to P before. P can be whatever we want here. Now, even if we don't know what P is, we know that it is a closed statement in Boolean logic. So as a result, if you think about what's going on, there are only two possibilities for it. So in this case here, everything in here, this represents all the possibilities. We want to make sure that every possibility has been taken care of here. Now, with in Boolean logic, there's only two options: true or false. So that means here we're going to be creating something like this here. This column P is our original statement, and there are only two possible values for it. It's either true or it's false here. So you can do that. Now we know that a true statement, right, if we negate it, if we put the negation in front of it, a true statement becomes false. And similarly, a false statement becomes true. So for something like this here, therefore, what we have is, as a result here, we have this sort of idea where we can just basically express what we just talked about here and express it in a rather compact statement here, where true statement, a starting true statement becomes false, and a starting false statement becomes true. And that is going to be our logical negation.